Welcome to Lecture 8 on how the embryo develops. Last time we looked at how in the 18th century there emerged a new system of classification for the diverse kinds of living things that were known at the time. We encountered the idea of a great chain of being that ran from the most primitive organisms at the bottom of the scale on upward through more and more complex beings until we reach humans. And it didn't stop there, it kept right on going up to the heavenly hosts until it came to God, the Creator. When the Swedish natural philosopher Linnaeus published his new system of classification for terrestrial forms of life, its usefulness became obvious pretty quickly. One reason why, in my opinion, was that it seemed to confirm the great chain of being. It was as if Linnaeus had spelled out the contents of the great chain. He'd begun primarily in botany, but his system could be and was applied to the animal world as well. Anyway, although, as we noted, not everyone agreed with Linnaeus' scheme, it gained widespread acceptance by the end of the century. We noted one other thing as well. I'm thinking how Linnaeus' ideas about how species had come to be changed over the course of his career. For those who went along with him on this, and many did not, it altered the way they thought of the great chain of being. In a word, the great chain was something that emerged over time. It was a historical process. For most, the great chain was something static. It was something you could imagine in your mind, almost like a real chain with links representing the species. Thinking of it this way, it was like an inventory of nature. With Linnaeus, it began to be something more dynamic. The links weren't all there at the start. They appeared over the course of time. The great chain of being in his scheme possessed aspects different from a merely static inventory of nature. They're better captured by the idea of a program of nature, a program that's played out over time. Well, today, our focus is still on the realm of living things, but this time, we're not going to be examining them as groups with an eye to classifying or arranging them. In this lecture, we'll be looking at them as individuals. Our particular interest will be in their development. In our last lecture, we focused mostly on plants. Here, we'll be looking primarily at animals. That's where a really interesting problem lies. This problem, like so many fascinating questions, originates in something we tend to take for granted. I'm talking about the process of growth. We know that reproduction in animals requires the presence of males and females. But how do we explain what happens after conception? How did naturalists explain what goes on during growth? See, most of us take growth for granted, but there's a real problem to be solved here. Take the embryo. Here's where we might be able to get a better grasp on the issue I'm referring to. The embryo appears to begin as a formless mass. Then it gradually takes on one of the many forms of animal life on our planet. In early stages, embryos resemble each other. But as they develop, they begin to differentiate into the vast number of animal forms that exist. The problem, in a nutshell, is this. How does one embryo know to develop into a rabbit and another into a horse? What guides the development? Maybe embryos don't begin as truly formless masses. Maybe they have structures that are already present. Well, you say, look, this isn't so hard. Embryos are merely following the laws of nature. But if the development occurs according to the laws of nature, are there as many different laws as there are animal forms? Is there one set of laws at work here? If so, what kind of laws are they? Are they laws of matter? Are they laws that are unique to living things? I hope you're beginning to see that this isn't such an easy matter after all. You won't be surprised to learn, I'm sure, that naturalists in the 18th century considered this problem, how the embryo develops. As in other subjects that we've considered, here too, there was an inherited wisdom on the issue. So, what views on these matters came down to naturalists of the 18th century from their predecessors? Here's how our old friend Descartes handled it in the 17th century. Like many others, he believed that females produce female semen and males a male semen. According to Descartes, male and female semen were mixed in procreation. The particles of the mixed semen then underwent a process of fermentation. The heart and other parts of the animal body slowly formed during this fermentation. Of course, you and I want to know more about how the parts resulted from fermentation. But alas, he doesn't tell us. Descartes simply asserted that the formation occurred without indicating why or how different adult forms came about. From everything we know about Descartes, I mean in particular how committed he was to the rules of mechanical laws in nature, we can be sure that he assumed fermentation involved the operation of mechanical laws. He just never said what those laws were. Well, that's a start anyway. There was another 17th century figure who weighed in on this issue of the growth of the embryo. It was a theologian named Nicholas Malebranche. Now, Malebranche appreciated Descartes' philosophy for the most part. For example, he acknowledged that mechanical laws were involved in the development of the embryo. But Malebranche denied that just the laws of motion acting blindly could somehow account for the differentiation that showed itself in embryonic development. To him, it just couldn't be that the embryo was really an unorganized, formless mass. His way around the problem was to assume that there was already structure present in the embryo. 1674, he proposed an extremely intriguing idea that adult forms were encased, preformed in the eggs of animals. That would solve the problem. You don't have to explain how the structure emerges if it's there from the start as part of what God was responsible for. But wait just a minute. If the organization of the adult form was present from the start in the egg, what do we need males for? What do males contribute here? Not to worry. There was a role for sperm. It took the sperm meeting the egg to unleash the gradual expansion of the form. And that's pretty much what growth was, the gradual expansion of pre-existing adult form until it reached its adult size. There's more here you might not have yet realized. These miniature adult forms that are contained in each egg, each in turn contained even more minute adult forms. And each of those also contained more adult forms. And that chain continued until all the future adults that would come in that line were accounted for. Before you say, good Lord, that's a lot of adults you're talking about, realize in the 17th century, the original creation was thought by a churchman like Malebranche to have been about 6,000 years earlier, and the future would not likely go on that long before the second coming of Christ would determine the end. And look at the advantage of this idea. Because all adults that would ever live were already formed in miniature, one didn't have to explain how the embryo knew the final form into which it was to develop. Now, this approach has been called the theory of preformation. I think you can see why. The adult shapes were preformed in the embryo. Preformation, then, is the belief that the adult form existed in the embryo of animals and that in growth it simply expanded. It was so neat a solution to the problem that at the beginning of the 18th century, preformation was widely accepted among natural philosophers. They concluded that God had encased adult forms at the original creation. Now, I want you to notice something here about what this theory does. It says that the explanation of why development goes in this direction is not due to matter itself, it's due to God. By itself, matter was powerless to act creatively. You could study the nature of matter from now till doomsday, and you would never, in their view, be able to explain from the properties of matter why it could take on the adult forms found in the embryo. One more thing. Preformationists did not deny that mechanical laws were involved. Once God's creative act had placed the adult forms in the embryo and the sperm activated the growth process, then after that, everything happened according to the mechanical laws that God had imposed on matter. They just did not think that mechanical laws by themselves provided a complete account of why the embryo unfolded as it did. Incidentally, some preformationists argued that it was the sperm, not the egg, that contained the encased adult forms. This was a minority view. Maybe some didn't like the majority view because it gave so much responsibility to females. Well, the majority was no less chauvinistic. The reason why the great majority denied the sperm the role of housing the encased adult forms was because, in that case, way too many future individuals would be wasted. Why? Well, if when males and females mated, it took only one sperm for each individual, you get the idea. As the 18th century progressed, preformation seemed to be doing just fine. In fact, in the 1740s, preformation in the egg as opposed to the sperm got new support by a scientific discovery. That happened when a Swiss natural philosopher named Charles Bonnet discovered parthenogenesis in aphids. Parthenogenesis is the reproduction of an organism without fertilization by a male. Bonnet showed that female aphids, also known as tree lice, could reproduce themselves for several generations without fertilization by a male. Since the males weren't necessary, the miniature forms had to be stored in the females. Of course, this notion of preformation couldn't go without major opposition forever. Right around the time of Bonnet's work, another discovery occurred that provided an occasion for a challenge to the theory of preformation. It was done by another naturalist from Switzerland. Well, that's a little misleading since Abraham Tremblay was born in Geneva, but at the time of his discovery, he was in Holland. When Tremblay first came across the freshwater polyp, he thought it was a plant. But then he noticed that it was capable of independent motion, so he concluded that it was an animal. He also discovered that the polyp could do something quite remarkable. It could regenerate a complete organism after having been cut in two. That in itself was astonishing, but it also implied that you didn't need a complete adult form at the start of things in order to produce an intact adult form. Here was a case when half an adult form was enough to reproduce a new complete adult. If you could do it here without a whole adult form, why did you have to have a complete adult form in the embryo? Preformation theory, of course, is based on the assumption that you do have to begin with the whole structure already there. Enter the Comte de Buffon, whom we keep meeting in these lectures. The fact that his name keeps coming up in so many different contexts should confirm for you his importance in the 18th century. He was indeed one of the leading thinkers of his day. When it came to the issue before us here, how the embryo develops, Buffon came out against preformation theory. His reasons, once again, were his own. Buffon said, look at the developing embryo. You don't see a tiny adult quickly emerge into recognizable form. That's not what happens. The embryo shows no change at all for a good period of time, and then the formation occurs gradually. Further, said Buffon, think about this. Offspring resemble both parents, so the mixing of the seminal fluids of both parents must be necessary to form a composite entity. A miniature adult encased in the egg, or in the sperm for that matter, can't explain why offspring bear a resemblance to both parents. Good point. But how then did Buffon explain the development? Well, it's not all that helpful, at least not in my opinion. Buffon said that nature must have provided what he called an internal mold that directed the development of the embryo. That doesn't do much to explain things. It just seems to push the question back to how this internal mold works. Are there as many different internal molds as there are different kinds of embryo? This kind of explanation reminds me of Descartes when he attributed things to fermentation, as if that solved things. I'm being a little harsh and judgmental here, I realize that. But my reason for being so is to underscore the difficulty of the problem. Whatever you think of preformation, it's hard to come up with a good alternative. Well, Buffon wasn't the only one trying to find an alternative. The big challenge was to get rid of the need for the pre-existing structure the preformationists said was in the embryo. But if you were going to do that, you were going to have to say that there wasn't a pre-existing structure present. That was in effect saying that the embryo was formless. You'd be saying that the development of the embryo into adult forms that are highly organized proceeded from material that was previously unorganized. This position has a name. It's called epigenesis. Epigenesis is the belief that the embryo develops from material that was previously unorganized. Those who held it, we call them epigeneticists, asserted that in fact the embryo does develop from matter that was previously unorganized into organized adult forms. Now, there was a famous debate between preformationists and epigeneticists that took place in the 1760s and 1770s. I want to tell you about it. In fact, this debate will concern us for the balance of the lecture today. It begins with the work of yet another Swiss naturalist. This one was Albrecht von Haller, a Swiss physician, journal editor, general polymath. Like Tremblay, Haller didn't stay in Switzerland for his education. He went to Germany and to Holland. Back in the 1720s, as a student in Holland, Haller learned preformation theory from his teacher. This was one of the earliest Dutch followers of Newton, famous physician-surgeon named Herman Boerhaave. I mention this for a specific reason because the Newtonian influence will turn out to be important, as we'll see at the end of the lecture. Anyway, when Haller heard about Tremblay's polyp in the 1740s, that's the animal you can cut in half and it regenerates back into a whole polyp, it convinced him that complete adult forms were not necessary for development, and he changed his mind. He became an epigeneticist. He accepted that the embryo was an unorganized mass. Becoming convinced that the embryo was unorganized was not, of course, the same thing as saying how then it did develop, and Haller didn't really try. It was more that he had become convinced that the preformation theory was deficient. Rather than try to explain how the embryo became organized as it developed, Haller merely stated that the development proceeded, and these are his words or close to it, according to laws that are unknown to us, but which the eternal wisdom has rendered invariable. We're beginning to see a trend here. The epigeneticists are better at opposing preformation than they are at spelling out epigenesis. But then something else happened. In 1749, when Buffon published his epigeneticist ideas about generation and internal molds, Haller read it and found himself disagreeing with Buffon at several points. He began to see that criticism of preformation was a lot easier than replacing it with epigenesis. Buffon's failure to defend epigenesis adequately, in his view, provided an occasion for Haller to reconsider questions of generation. And reconsider it he did. For 3 summers in the mid-1750s, Haller conducted a series of experiments on incubated chicken eggs. He followed chicken eggs in the various stages of their development, kept careful records of what he saw as the chicken embryo unfolded. During this same period, he was also in correspondence with the preformationist Bonnet, Charles Bonnet, whom we met earlier. Bonnet encouraged him in his experiments. Haller observed that the membranes of the yolk were like the membranes of the intestines of the developing embryo. And from this, he concluded that the yolk was but an expansion of the small intestine of the chicken. He was coming back to preformation theory. What sealed it for him was that the yolk exists before the male approaches it, so the female must possess the true beginnings of the fetus. Haller announced his reconversion back to preformation in a letter to Bonnet in September of 1757. The next year, 1758, he published his conclusions to the wider world. Haller's publication stirred the pot, so to speak. It wasn't long before a reply to Haller's announcement appeared, and it came from a young German physician in Berlin named Caspar Friedrich Wolff. Wolff strongly supported epigenesis. He just defended it in his doctoral dissertation, so he was thoroughly committed. He was a confident young scholar, and as confident young scholars sometimes do, he wanted to make sure that one of the leading figures in the field knew of his work, even if that leading name had just published a contrary view. Maybe that was the attraction. Maybe he felt that he, the brilliant young doctor, could show Haller why he was wrong. Anyway, he sent a copy of his dissertation off to Haller. Now, Wolff's theory of epigenesis was quite a bit better spelled out than that of Buffon or that which Haller had once defended. He argued that the embryo developed as the result of a process of solidification of fluids. Let me explain that a little more. He thought fluids were secreted in the embryo and that they then solidified into structures. He began with the yolk. The process of secretion, followed by solidification, proceeded in serial order. Each part of the developing embryo, once it formed by solidification, secreted the next after it, and so on. After a part was formed, there was a flow of new fluids into it that produced vessels, and so its organization was defined as it developed. Now, Wolff didn't just dream this up. Like Haller, he had conducted a series of careful observations that formed the basis for his conclusions. So Haller and Wolff both appealed to empirical observations to substantiate their respective claims. For example, each asserted that careful observation of the formation of the heart justified his conclusion. It was just that they came to opposite results. Haller said that what he saw from his observations clearly showed that the heart was preformed. Wolff, on the other hand, said from his observation it was clear that the heart was not preformed. Now, how do we make sense of this? How do we explain the different ways in which Haller and Wolff read the same empirical data? One way to understand the different interpretations that Haller and Wolff made of the same empirical observations is to look at their differing philosophical positions. Now, we're going to get a little philosophical here, but it will help us see why Haller and Wolff saw things so differently. Let's start with Haller. His position is entirely consistent with the Newtonianism he inherited from his teacher, Boerhaave. That's why I mentioned earlier that what he learned from his teacher in Holland would be helpful to us later. Well, how does this work out? Haller admired Newton greatly, and he was very much like him. For example, he employed mechanical laws to describe nature, but he didn't think that merely the operation of mechanical laws by themselves was sufficient to explain why nature behaved as it did. Neither did Newton. Recall that for Newton, God had to be present in nature. God did not exist apart from nature, as in the deist's position. God was part of Newton's natural philosophy. For Haller, too, God was a necessary part of the explanation. Yes, we must look for mechanical laws in the operation of the expansion of the miniature adult forms in the embryo. But we must recognize God's role in the placing of these forms there, and we must do it as part of our explanation, as part of preformation theory. God was part of Haller's natural philosophy. Note that Haller was not attributing any active power directly to matter itself. It wasn't the matter that possessed the capacity to develop on its own. Like Newton, Haller believed it was dangerous to attribute active forces directly to matter. Matter itself was passive. If matter possessed active forces on its own, forces that could direct the development of the embryo, for example, then that removed God to a distance that made Haller uncomfortable. To push God away like that invited godless materialism. So Haller allowed for mechanical expansion of embryos, but insisted that God was responsible for the original organization that expanded to form adult individuals. This was how, then, Haller reconciled his belief in mechanism with his religiously motivated opposition to materialism. It was very much like the way Newton had done the same thing. Well, what about Wolff? Where was he coming from? Wolff had been trained in the philosophy of Newton's rival, Leibniz. He saw his position as an natural outgrowth of the Leibnizian heritage he embraced. Now, I have to be clear about something here. Wolff's epigeneticist views were not required by this heritage. What I mean is that just because he was a follower of Leibniz didn't mean automatically that he had to be an epigeneticist on the question of generation. But he himself did think that his agreement with Leibniz entailed the epigeneticist view. And what he believed to be the case, that's what's important. This is not the place to go into a philosophy of Leibniz in order to show you that You could be a Leibnizian and defend pre-formation, but we don't have to do that anyway. The important point again is that Wolff himself thought his epigeneticist views were supported by his embrace of Leibniz's philosophy. And in fact, it certainly is possible to interpret Leibniz in a way that makes epigenesis entirely consistent with his view. Let me see if I can explain how Wolff saw things. We also met Leibniz briefly in Lecture 2. There we saw him primarily as a critic of Newton's idea that God occasionally stepped in to set things right when the cosmos was getting out of whack. But another big difference between Newton and Leibniz had to do with their differing conceptions of matter and force. Newton was convinced that matter by itself was passive, that it had to be animated by a spiritual activating agency. Otherwise, he thought, you could let matter explain everything there was, including spirit. That to him was materialism. When matter took the role of God, it was atheism. Now, Leibniz had worked out an elaborate metaphysical position in which matter itself did possess active agency. We won't go into his metaphysics except to say that Leibniz was an idealist, by which I mean that for Leibniz, reality was at bottom ideal. That meant not only that mind took precedence over matter, but that matter was ultimately derivative from mind. And that meant it was entirely reasonable to speak of matter in terms that also applied to mind or soul. The other characteristic of Leibniz's philosophy that is important for us was his firm conviction that human reason was capable of giving a complete account of reality. He purported to incorporate knowledge of the physical and spiritual realms into one idealistic system that was rationally consistent. To some, that seemed a bit much. Many of you know of Voltaire's novel Candide, in which there's a character named Dr. Pangloss. Pangloss is the one who argues that this is the best of all possible worlds. From his name, Pangloss, you get the idea of what Voltaire thought of Pangloss's claim. Anybody who says he can explain and justify everything as rational, including physical and moral reality, was fooling themselves. Now, I said that Caspar Wolff had been trained in the Leibnizian tradition. He was, but he had not been trained by Leibniz himself. Leibniz had been already dead for almost 2 decades when Wolff was born. Wolff learned the Leibnizian philosophy from the work of Leibniz's chief follower and exponent in the 18th century. This was, ironically enough, another man named Wolff, Christian Wolff. Christian Wolff elaborated on and expanded the philosophy of the master and made it more palatable in the process. Christian Wolff's rationalism became enormously popular at Halle University, where he taught. Now, our man, Caspar Wolff, arrived at Halle a year after Christian died, but he studied Christian's works and determined to be the first person to apply the principles of rationalism, as Wolff's philosophy was called, to embryology. You may have been wondering where we're going with this little philosophy lesson. Well, it turns out to be very relevant. Here's how. In his defense of epigenesis, Caspar Friedrich Wolff rejected the separation of matter and spirit into 2 distinct categories. He was, like Leibniz, an idealist. He explained matter as an aspect of mind. That meant that he could attribute to material process qualities men like Newton and Halle reserved for a separate soul. Wolff denied that the embryonic development was guided by a soul separate from matter, directing it from the outside. He insisted that the physical processes of secretion and solidification were themselves sufficient to explain embryonic development. He believed, in other words, that the realm of the material where the physical processes of secretion and solidification occurred possessed in itself the directive agency needed to guide the mysterious development of the embryo. In the end, the conception each had of God's role provides a helpful means of distinguishing their views. For Halle, God had to be directly involved. In this, he resembled his predecessor, Isaac Newton, who insisted that God was directly involved with nature. Wolff objected to the pre-formationists' direct appeal to God's interference with nature. Like Leibniz, who objected to Newton's appeal to God to interfere when the cosmos required it, Wolff did not like the pre-formationists' appeal to God's role in embryonic development. Wolff preferred, as he put it, and these are his words, to show that the finished plant is not something to whose production natural forces are completely insufficient. Preformation theory, as enunciated in the 18th century, eventually passed from this stage. We'll see how that happened in Lecture 13, when we discuss the birth of the new science of biology. That will bring with it a new way of handling development in nature in general. The other difficult issue, what is God's relation to nature, that one remained very much alive for a long time. It will resurface again, as we'll see in future lectures.